Morning all. Welcome to the second day of National Conference on Emerging Frontiers in Chemical Sciences. Today we have 7 technical sessions, 4 in the forenoon session and 3 in the afternoon session. The first session is by Professor Rajakumar Balla. I welcome all the participants, speakers to the second day of the conference. I also welcome Dr. P.K. Sajid for chairing the first 2 sessions. Thank you.
Thank you, Dr. Rafiq. Good morning, everyone. I am here to welcome Professor Rajakumar Balla. Professor Rajakumar Balla is currently working as a professor in the Department of Chemistry, IIT Madras. He qualified PhD from IASC, Bangalore, and he published more than 80 research articles. His research interests include atmospheric chemistry, combustion chemistry, and computational chemistry. Professor Rajakumar Balla received several honors and recognitions. He is a fellow of RSC and is a recipient of CRSI Bronze Medal. He has been a visiting professor at various universities and institutes. With this short introduction, I welcome Professor Rajakumar Balla for this talk.
Thank you, Dr. Rafiq and the college administration to call me to give the presentation. Here, let me share the, is it in full screen mode?
It is not yet.
Yeah, I am view slideshow. Am I missing something? It is not coming.
At the bottom, you will see.
No, it is not seen. That's the thing. In the top, where is that? View. Slide shorter. Slide master. Can I just exit?
No, slideshow. View.
Fine.
Yeah. 1 minute. I don't know why it is happening. Yeah, view slideshow.
Yeah, next to before view, whatever button you are clicking before that.
Yeah.
2 things before.
Yeah, from current slide. Yeah. Can you see?
Not yet. You have to select it.
One moment, please. Okay, I don't know. Are you able to see now?
Has come, but not full screen.
Yeah, it is taking time for some reason.
At the bottom, yeah.
Yeah, I've done it. Yeah.
All right, good.
Yeah, sorry for the first minute delay. Thank you very much, Dr. Rafiq, Dr. Kavita, and all others. Professor Pradeep, particularly, I could see in the invitation it was copied to me with Professor Pradeep, whom I really admire and love a lot, my dear colleague, and college itself. I'm very much thankful to you for this given opportunity. Now, what I'm going to talk about is the measurement of absorption cross sections in the kinetics of radicals relevant to the Earth's atmosphere using unique facility, which is called cavity ring spectroscopy. People who are attending this can always write to me at this email ID, and my websites are given here. I will be able to I will be very happy to answer your queries later on after the talk. Now, what I do in my research laboratory is, as Dr. Rafiq and his colleague has introduced, I practice two areas. One is combustion, and the other one is atmospheric science. And both I go with the experimental methods as well as the computational methods. I will describe today purely the atmospheric processes, how we work on, and what problems we are identifying, and what problems how we are dealing with those problems. I'm going to talk about it today. And when the minute you talk about the atmosphere, first thing that comes to our mind is ozone. Therefore, I start there. Ozone in the Antarctic region, all of us have heard of the loss of ozone in the atmosphere, particularly stratosphere, particularly southern hemisphere. So if you look at the picture, if you take the globe and hold like this and look at from the bottom, and what you see is the atmosphere just above the bottom, that is southern hemisphere, you can see a deep blue area, which is essentially the loss of ozone in this particular region is very, very high. And it was identified to be 10.6 square million miles, which is essentially 27.5 million square kilometers. That was ever largest, which was observed in 1st October 1998. And when you go from here, away from the center spot, you can see the blue, darkness of the blue reduces, and finally it becomes red. So essentially we are going from blue to the red spectrum. That means red area is full of ozone and blue area is loss of ozone. The color code also, to dissociate ozone, you need ultraviolet radiation. That was the thing. Therefore, with this, a lot of attention was paid on why this has happened. What are the reasons for this to happen? What are the remedies to look into this, solve this problem? These thoughts came into picture right early 1990s. And then many people worked on that. And these three individuals, Professor Molina, who passed away recently, Professor Crutzen from Mainz, Professor Roland, he also is no more. These three individuals worked on the loss of ozone in the stratosphere and generation of ozone in the troposphere. They got Nobel Prize for their work in the atmospheric chemistry, particularly concerning the formation and decomposition of ozone. So when we talk about ozone loss, we need to know the reasons also. When you look at the reasons, the first implication that we can see right just before the lockdown and after the lockdown, you can see the Himalayas from Chandigarh. You look at this. There were absolutely, you can't see any of the snow or anything. And just to start off the lockdown, people started seeing this. And after 1 month, it was fantastic view, spectacular view. People have even better quality pictures. Personally, people have sent me. And that kind of clarity was possible because of photochemical smog was reduced. That was the reason. Why this photochemical smog is being formed? What are the reasons for that? I will go through them little bit in detail. And one more picture, which we all love to see. This is in front of Rashtrapati Bhavan. When you stand, you can see this India Gate. And just before the lockdown, this was the situation. During the lockdown, this was the situation. This shows how much photochemical smog actually disturbed Delhi people. Not only Delhi, for that matter, any places where a lot of activities are there, particularly the vehicular emissions. So if that is the case, we should always question what are the reasons for this. If you look at the composition of the Earth's atmosphere, particularly the chemical composition of the Earth's atmosphere, you have 21% of 20.6% of oxygen and rest all 1.4%, and 78% of nitrogen is there. Whenever we are breathing, 78:20. That we know. But this 1.4 matters a lot. What are the reasons for that? What are these compounds? If you look at right from argon, most abundant. If you go to CFCs, it is 1 × 10⁻⁷%, which is essentially very, 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 very low concentration. But the influence of that is very, very, very big. Therefore, we need to understand what happens if these compounds are released into the atmosphere. These greenhouse gases naturally have a serious implication on our biosphere. Therefore, we need to look into the details of what exactly the chemistry which happens after the release of these compounds into the atmosphere. If you look at the chemistry, the emissions can be any source: industries, landfills, volcanic eruptions, man-made emissions, which are essentially called as anthropogenic. And then it is not just emission, but also whenever something is emitted, it has to be dissipated. Once it is during the dissipation process, depending upon the height at which the compound is existing, in other words, how long the compound can reside in the atmosphere, that decides the height at which, or the place at which, or the zone at which, or the region at which the compound is there. And once the compound is there, it gets activated and chemistry gets activated, particularly in the troposphere, at the edges of the troposphere and the stratosphere. What happens is the compound gets exposed to the light, and therefore, depending upon their absorption cross sections, how big it is, the thermal free radical formation generates. Happens. The photochemical radical formation happens, both temperature wise as well as photochemically. Once these radicals are formed, you cannot we cannot even think that heterogeneous chemistry is possible in the Earth's atmosphere. You may ask me, Rajkumar, you are talking about the gases, but where is this heterogeneous chemistry is coming into picture? Polar stratospheric clouds are the clouds which actually floats like pellets over the stratosphere or just below the stratosphere. And these compounds, wherever there is a cool atmosphere, like us, molecules also prefer the cool atmosphere. They go and settle over there, and the chemistry starts. The chemistry starts when sunlight comes into picture, particularly the ultraviolet radiation. And once the radicals are there, what we need to understand is that is one way of formation of the radicals. The second way of formation of the radicals is they can be reacting with the highly abundant oxidizing species such as hydroxyl radicals, chlorine atoms, and many other nitrates and other stuff, ozone. And when hydroxyl radicals are there, chlorine atoms are there, hydroxyl radicals are particularly referred to as the detergent of the atmosphere. Actually, it washes out all the compounds that are released into the atmosphere. Therefore, once hydroxyl radical reacts with the compound, it grabs one of the hydrogen and leaves the radical. Now, I come back to my original point. First thing is, it can be photodissociated and form the radicals. Radicals can be formed. The second one is, it can react with the hydroxyl radicals or chlorine atoms or oxidizing species and form the radicals. The formation of the radicals is for sure. So now what is that? How fast these radicals react with the compounds determines how efficiently the photons dissociate the molecule, determines the lifetime of that particular molecule or those particular molecules in the atmosphere. That is what is called the atmospheric lifetime. This is not the lifetime what we are talking about in the excited state. That is a different story. Therefore, we need to measure one thing, the photochemical properties, that is absorption cross sections, quantum yields of the radicals, that is on one side. Second side is the kinetics of the OH radicals. Is it only a OH radicals? Once the radicals are formed, what happens to those radicals? The radical reactions and radical molecule reactions, many reactions have to be studied to understand and model the atmospheric chemical composition. Therefore, I move on to the topic, how do we study the radical reactions, radical molecular reactions? First, I will talk about the radical formation and the reactions of radicals. Before I go into that, we need to understand the atmospheric composition. This is a well-known thing. Only thing which is not known to many non-scientific people is like, well, all of us know that when you go into the upper altitudes, we can see the drop in temperature. But what has to be understood is it is not exactly like the way the pressure is changing. With every 10 kilometers, you lose 1 0. If you talk about one bar is 1000 millibars, for every 10 kilometers, pressure drops down by 1 0. That is, it is linear, but temperature is not like that. It is going decreasing, and then again increases. So there are a lot of reasons. We will not get into that, but I emphasize to show this because we need to study the kinetics in this region of the temperature and this pressure. This is very important. It is not that we just take some molecules and generate radicals and study, but we actually mimic the atmospheric conditions in the laboratory. That is what I wanted to emphasize upon. And now, what happens when the compound is released into the atmosphere? Here is the key point. It reacts with hydroxyl radicals or photon, as I told you in my first slide, and it forms the radical, reacts with the oxygen and forms the peroxide radical, and reacts with NO. On another side, it also reacts with RO2, and essentially it forms the ozone here. And if it goes to the upper atmosphere, they form the compound forms carbonyl compounds, alcohols, and all kind of. Once you release a compound, actually it is going to create a chemical mess in the atmosphere. That's what is the precise point. Now, how do we study how one can measure the absorption cross sections of these radicals? The best possible solution is cavity ring down spectroscopy. So cavity ring down spectroscopy is a unique technique, which I'll describe it in detail here. Then I will go into the scientific topic. And now, if you look at this, what we generally do is take two highly reflective mirrors, and highly reflective in the sense the mirror I have pointed out here, I have shown here, it's about 99.999% of reflectivity, and such two mirrors are arranged in a collinear fashion. The angle between both of them is absolutely, zero. And when you do that, when you pulse a photon into the cavity, which is essentially forming a Fabry-Perot cavity, and it gets into 99.999% of the light gets reflected back. However, 0.0001% of the photon gets in, and it goes and tries to go out of this cavity, but unfortunately it faces another dirty mirror, which is also 99.999% reflective. Therefore, it reflects back 99.999% of the light back into the cavity and leaks out 0.0001%. So here the catch is, it leaks out 0.0001% of the 0.0001% of the exit from the first mirror, which is actually 0.0001% of the total intensity. And by the time it is naturally dead, the photon is dead, it would have crossed a path length close to 50 kilometers or 100 kilometers, depending upon how nicely you align these two mirrors. And the light, if you detect, it would be exponential, and that is red one. If you put some chemicals over there, the decay is blue. So essentially, all the information what we get is the decay with and without chemicals. That's all it is. This is the Beer-Lambert's law, nothing else. Now, I have made a small animation for people who want to understand this. You look at this, a big photon, 99.99% is reflected, but this photon is trapped inside. You see that it tries to go to and fro, and it doesn't have any other job other than running between these two, because it is trying to exit from the other window. It's not happening, and you see it is a tau zero. If you put, that is the ring down time constant without any chemicals. But as I told you, we are chemists. We want to see what happens if you put the chemicals over there, and this is what is tau when you put the chemicals over there. When you see that, all you get is tau and tau zero. If you just modify the Beer-Lambert's law to the convenience of viewers without changing the units, what you get is, it is a relationship between the absorption cross-section and absorption, and also the tau and tau naught. And here is the catch. The spectrometer is a super sensitive, optically super sensitive, because it has a path length of about a minimum 50 kilometers and a maximum of 200 kilometers in a cavity of 1 meter. So you can ask me, so if the path length is so high, Beer-Lambert's law gets saturated, right? Therefore, how do we do that? If you take the Beer-Lambert's law, A equals to epsilon LC, if you plot absorbance over the versus the concentration of the species, what happens is you should see a straight line no matter whatever the concentration is. But it doesn't happen like that. Because of limitation of the detector, it gets saturated. Therefore, you will have believable results in this region and absurd results in this region. So these results cannot be believed. Therefore, what you need to do, your absorption cross-section is constant, epsilon is constant, path length is almost fixed now, and what is the one what you need to play? Concentration. So to make it to be linear in the region of your measurement, you need to come down with the concentrations at least several orders of magnitude, 7 orders of magnitude, right? 100 million like molecules you have to reduce. You can ask Mr. Rajakumar, why are you struggling to increase the path length? And why are you coming back in the concentrations and reducing? Essentially, this is the point we want to hit. The point here is we wish to see mimic the conditions in the atmosphere in the cavity of the ring down spectrometer, that we can actually see the concentrations of these species are not more than parts per million, parts per trillion. So therefore, the sensitivity of your spectrometer should be very high to detect such kind of low concentrations. Therefore, this exercise is. And once we have this is the spectrometer what we have built. You can see all these are arranged in a very the convenient way for us. But if you put everything into a box and sell it, we can call it as a cavity spectrometer. And except the lasers, everything else, lasers and optics we purchase from outside, everything else is designed over here. And now we have actually now built the spectrometer. Now this is the typical ring down profile. And then when you go into, now as I told you, we need to worry about the radicals. How do we generate the radicals? Here our chemistry starts. Now I have the probe beam, that is the cavity ring down beam, that is CRD beam, which probes from one mirror to another mirror, which travels. But I want to generate the radicals, so I put another laser and in perpendicular direction. Or many ways we can do. This is the best way what we have figured out. And when you generate the radicals, you should understand when you are generating, you cannot fire two lasers and expect the reactions to happen. Now what we need to do is we need to talk to these two lasers with a delay generator. That means I will say, I will probe, I will fire a laser and ask the laser to produce the radicals, and I will fire another laser after certain amount of time and ask that laser to probe the compound which is there existing in that. After generating the radical, we can probe at several intervals. You can ask me why. The several intervals, what does it mean? After producing the radical in presence of another chemical compound, you can actually go into the kinetics mode. You are actually giving the radical to live for a long time, react with the existing species. After all, kinetics is the variation of concentration of the species with respect to time. Once you have that, you have the kinetics. Suppose if you don't give a delay between these two probes, these two beams, then you can actually measure the absorption process. You are not giving a time for the radical to react with the species around it. As soon as it is formed, you are probing around. So the beauty of this is you can actually measure the absorption cross section, you can measure the quantum waves, and you can measure the kinetics of radicals with stable molecules and radicals with radicals. I will take one example in each case, and I will describe now. So basically, this is the spectrometer what we have built. You can see the cavity over here. It is going all the way, and in a close view, this is the cavity, the long one, and the short one is the photolysis beam path. These two are perpendicular to each other. Okay. Now this is the typical view of working bench. Lot of exercise involved. About a decade we have worked to build all this, and finally we are all set to go in an autopilot mode. Now I will show you a beautiful spectrum. Now you can ask me, okay, you have built, so what? So what is the sanctity of your spectrometer? Well, we have taken the HCO radical spectrum, which was published by John Vlad, and then I told my student, okay, let us measure this. Let us do the litmus test. Trust me, point to point, we could reproduce the spectra. You look at the resolution of the spectrometer. It is 613.8 to 615.8. Just 2 nanometers. We could scan up to 0.0001 nanometers. That is, the resolution of the spectrometer is 0.0001 nanometers, which means 2 lines which are separated by 0.0001 nanometers. My spectrometer can see those 2 lines essentially as 2 different lines. That is the beauty of this. Why? Tomorrow, I want to measure the kinetics of the radical at a particular wavelength, because I want to probe those radicals at tuning my laser to a particular wavelength. My wavelength can be as specific as it wants. So this litmus test is done. I said, fantastic, let us go ahead and do. Now I will show the worst part of the spectrum. I'll just show you this. You can see the resolution, how nice it is, right? I will show you. This photochemistry of propanol radicals. As I told you, propanyl radicals are the radicals which are essentially formed in the photodissociation of the acetaldehyde or OH radical reactions with propanylaldehyde. Sorry, it is not acetaldehyde. And then you can generate these radicals, and you can generate these radicals in many ways. OH plus these H bonds which are red colored, they are going to be cleaved, and you can use propanyl chloride and diketone, or you can use any of these, and you can produce the hydroxyl radicals using hydrogen peroxide at 248 nanometers. And these 248 nanometer production uses of 248 nanometers on hydrogen peroxide gives 200% of quantum yield of the hydroxyl radicals. So it is a neat experiment with a single 248 nanometer source. You can actually generate OH, and then it reacts with the propanylaldehyde, and it abstracts the hydrogen and forms the propanyl radical. So essentially, one bullet and two birds. We are having this kind of setup here. Therefore, it's easy for you to generate the radical. So using that, what we have done is we have measured the absorption cross section. This is the way we have done is we have actually used the hydrogen peroxide for the generation of OH, and we have used the two pulse, there is a 2 hertz frequency we have used, and I will explain this plot. When actually there was nothing in the spectrometer, that is essentially is a blank one. These red points are continuously just very stable, and cavity is very stable. Now the minute I turn on the photolysis laser, the hydroxyl radicals are formed, and therefore propanyl radicals are formed, and you can see there is a drop in the ring down time. And then I further increase the concentration of the hydroxyl radicals, and then you can see the further drop in the hydroxyl radical ring down time because of the generation of more propanyl radicals. And then I again try to come back by reducing the concentration, and further reducing, I came back to this. Therefore, I want to confirm what I am absorbing is essentially the propanyl radical. It's nothing else. Okay, now we can actually calculate the concentration of the propanyl radical using various mathematical, like you need to know the concentration of the precursor. And once you know the concentration of the precursor and absorption cross section in that particular wavelength, and you can quantum yield of that particular radical, and also you can, if you know the absorption cross section, you can fluence of the laser, you can calculate the concentration of the radicals. So essentially, the bottom line is we need sigma of that, but that is the essential component which we need is the absorption cross section. That's what we want to measure. So we have measured the cross sections not at one wavelength, but over 555 to 597, 597, yeah, plotted up to 595. But you can see the spectrum very featured. So each line is important. As I told you, when you go with 2 nanometers, you can see a lot of resolution. But here, the reason for that is, if you can arrest the free rotation of the methyl radical over the propanyl radical, that would actually reduce a lot of noise. And if you further arrest the rotation of the ethyl radical over the CHO, then the resolution of the spectrum can be much better. Once it starts rotating, you will have the the equilibration over the vibrational modes, and many things can happen. The energy exchange can happen. Therefore, we don't know what exactly is we are probing. Therefore, we have measured this, and I will show you when we have also varied the concentration of the radicals with respect to the when we are measuring the cross section, we wanted to see, is there any influence of the concentration of the radicals? You can see it is absolutely linear, and we are happy with this perfect absorption cross section we could measure, that is 7.9 into 10 to minus 20. That is very low cross section at 556. Therefore, you can tune the laser for this particular wavelength and start doing the kinetics. And then we also have seen the influence of the concentration of the precursor source, that is, this is actually propanylaldehyde. There is a typo. Propanylaldehyde concentration versus the sigma. If you see, there is no dependence. And we have also seen the fluence of the laser. We have changed, varied from actually 9 millijoules per centimeter square per pulse up to 15, and it's a lot. And we don't see any difference in the absorption. So with this, I will just move on to another example where we have measured the absorption cross section of xylyl radical. Xylene is one of the isomers that is it is used as thinner, solvent, agricultural spray, or adhesives, and it is used in the synthesis of various polymers and plasticizers, and it is used in the pharmaceutical industry, perfumes, polyester resins, and fibers. And orthoxylene is mostly, most widely used isomer. Therefore, once it is released, it forms the orthoxylene radical. It's a resonance stabilized radical. That means the radical is going to stay for a long time in the atmosphere. Therefore, we wanted to measure this. And when we measured this, what happened is like we wanted to measure the kinetics of the radical with various compounds. But what we have noticed is the reaction of these, radicals with the stable molecules is very, very slow. 10 to the power of minus 15, minus 16, because it is resonance stabilized. It tries to be, live like very long time rather than reacting with any other component. And we have actually used oxalate chloride to produce the chlorine, and then it reacted with this one of the hydrogen and produced the oxalate radical. And if you look at the spectrum, it is actually the resolution of the spectrometer. What we have I told you is 0.0001 wave numbers, but still I couldn't see any features. But we have used therefore what we have done is we have decided to measure with 2 nanometer resolution, that is step size, and then we have measured. Therefore we are not losing any information, and we checked it with 0.01, 0.001, 0.0001 nanometers, but nothing we have seen. Therefore, wastage of time and lot of energy, lot of resources, lot of students' time. Therefore, we are confined to 2 wave numbers, and this is the feature of the spectrum. And you can see at particular 468.3 nanometers, we have measured the cross section of this radical to be 10 to the minus 18. That is 2 orders of higher than the propenyl radical, because it is highly stabilized. It can absorb more. Okay. And then the interesting feature is the effect of temperature we could see on this radical at that particular wavelength. And what we have seen is when we change the temperature from 300 to 800 Kelvin, we have studied from this region is not reported. This one is somebody else has theoretically have calculated this, but experimentally what we have done is we have measured this, and we could see we are not interested in higher temperatures. As I told you, the temperature relevant to the atmosphere is very, very low. Therefore, we have confined temperature up to 320, 325 Kelvin, and then we have seen it is following what was reported. And then the temperature, the decrease in the cross section is very unusual for the this kind of transitions, like non-bonding to pi star transitions. Very unusual. The temperature dependence is there. Therefore, the decrease of the ground state vibrational population as well as the rotational population could be one of the reasons for this kind of unusual behavior. And also, we have changed the pressure. When we change the pressure, we could see not very significant, but definitely it cannot be neglected kind of thing. We have seen a variation. It's going down. Therefore, it could be because of the droplet broadening or even number density of the radicals, which are because of the at high pressures. What happens is velocities because of the flow velocity, a lot of collisions might happen, and the concentration should be varied between the varied from pressure to pressure. Therefore, that could actually influence the loss of the absorption. That is the explanation for this. Now we have done a low temperature gas phase kinetics of phenyl radicals with methanol. As I told you, absorption cross sections are measured. Those kinetics I'm not going to discuss. Now what we have done is phenyl radical we have taken, and methanol is one of the most abundant alcohol, and we have wanted to do, and we have measured this. It was very nicely done. As I told you, the phenyl radicals are very polyaromatic hydrocarbons are released into the atmosphere. Toluene, benzene, xylene, all these are released into the vehicular emissions. Therefore, phenyl radical formation is very, very abundant, and therefore we have taken up this study. And also, a lot of alcohols are being used today as one of the blends into the biofuel, regular fossil fuels. Therefore, alcohol emissions are also very high. Therefore, we have taken the study of starting from methanol and ethyl alcohol. Also, we have done, and we have the studies reported. There are 2 kinetics for the 2 reports are there. One is minus 10 to the minus 17. The other one is 10 to the minus 11. Therefore, about 6 orders of magnitude difference is there. So I don't know which one to believe. Therefore, we have measured these kinetics with a laser repetition rate of 2 heads. You can ask me, why do you vary the laser repetition rate? It is simple. When the flow system is going on, you have to make sure the radicals which are formed are actually probed in the next pulse. You don't want to leave any garbage, which is any baggage which is left over the previous pulse. And all other conditions are given, but the emphasis is to record the spectrokinetics in the very low pressure areas, where, because we, as I told you, we wanted to study the kinetics in the low pressure region. Okay, so all other settings are same except these 2 points I want to emphasize. And we have studied the kinetics. See, look at this, the variation of the concentration of the phenyl radical with respect to time without any reactant in the first one. And I started increasing the concentration of every time at a given temperature. You can see a pseudo first order loss rate. And we carry the reactions in a pseudo first order condition, and to avoid any secondary chemistry. Yeah. So now you fit all these 6 lines, and you have 6 data points at one temperature. And I have conducted we have conducted the experiments at various temperatures. You can plot all of them, and essentially they all should go through 0. But you can see an intercept here that shows there is a little secondary chemistry which we worried about it, and we have done the computational studies. What could be the reason and all? I will show you those secondary chemistries little later. Now, if you look at these reported kinetics, and mostly on the experimental studies, but this is the temperature region where they have not studied, and we have measured these kinetics. And now we have also studied the laser fluence and the pressure variation. All these litmus tests have to be done to make sure that the data what we produce in the laboratory is authentic. So we have seen the complete independence of both the pressure as well as the laser fluence, and therefore we can comfortably say the kinetics what we measured as are reasonable. And then we have, as I told you, to see the secondary chemistry effect, we have done the computational studies at various levels of theory. And one of the thing which is more towards the oxygen, the hydrogen which is projecting, which is actually one of the transition state, the alcoholic oxygen, which is more labile thermodynamically as well as kinetically, and this one was contributing, and we cannot neglect the contribution of all others. Therefore, we have taken the contribution of these things also into picture, and that could affect not really secondary chemistry within the intramolecular influence on the kinetics. Therefore, we have measured computationally, we have calculated computationally, and we have measured experimentally, and we know the other channels contributions also. Mostly it is 99% from the oxygenated hydrogen, and rest is all from the other this one. So due to want of time, what I will do is I will skip all these. What I will go ahead and I will show you is another particular radical kinetics, and then I will stop. Okay. Now, if you look at the BRO and peroxy radicals, both are radicals. Please understand that. And it is very difficult to measure the kinetics. What we need to do is we need to produce BRO as well as ethyl peroxide, alkyl peroxide. So we have produced the BRO using ethyl bromide in presence of oxygen and bromine. It produces, BRO. BR2 and oxygen, and it produces BRO. And ozone also we have used, and therefore ozone produces O-singlet and reacts with Br and forms BRO. And this ethyl bromide, when you use ethyl bromide, it produces ethyl radical and reacts with oxygen to form the peroxide radical. Now we have measured the cross sections of the BRO radical. You can see a systematic, two absorption peaks, and you can actually this is an advantage for you. You can tune the laser at this point or this point. Okay, that is the beauty of this. And we have done the kinetics when these kinetics were measured. So beautiful pseudo first order kinetics and exponential decay. And then we have measured this at various temperatures, and you can see how beautifully you can, as I told you, this is a unique facility where you can actually measure the kinetics, where actually you can measure the absorption cross sections, quantum yields, and many more things. How much time do I have? May I ask you?
3 more minutes.
3 more minutes, just fantastic. Okay. So I will just go to a similar laser technique where I want to show you something called laser induced fluorescence, which is known to all of us, but how do we do the kinetics is something we need to understand. When the molecule, when the radical is fluorescing and when the radical is not fluorescing. Non-fluorescing cavity ring down spectroscopy you can use. When it is fluorescing, you can use laser induced fluorescence. I'll explain you. When the hydroxyl radical is produced, you see this? At 282 nanometers, you can excite from lower ground electronic state to upper electronic state. And then from it will at 208, when 282, when you excite, it is emitting at 308 nanometers, is low energy. And another one is non-radiative transfer. And from there to here, it is another 308. Therefore, when you excite at 282, it is fluorescing at 308. You can put a band pass filter and measure the fluorescence. That is laser induced fluorescence. Then that is what is the technique what we have designed. Excuse me. And you can measure the kinetics using the same setup. Only difference is you have a photomultiplier tube here instead of a with a 308 band pass filter to identify the fluorescence. Of course, the intensity of the fluorescence is directly proportional to the concentration of the radicals used in the system. And with the variation of time, you can actually see the loss of concentration with respect to time, and you can measure the kinetics. And we have used such a, this is the cell what we have designed. It is a circle, you can use the circulation inside this one is a jacket and photomultiplier tube above and with a 308 band pass filter and one set of windows for 248 nanometers. This is krypton fluoride to use hydrogen peroxide photodissociation. And you can probe these radicals using 282 nanometers. You connect these two, as I told you, with a delay generator to vary the delay between the lasers. And this is what we have done. And when we have taken this particular system, trifluoro 222 trifluoroethyl butyrate with the hydroxyl radicals. When we have done it, only I'm talking about hydroxyl radicals, not the chlorine one. And we have seen this is the measurement when we have done without any substrate and with lot of concentration variation. You can see the exponential decay, and you find the pseudo first order loss. And with respect to temperature, you can measure. We have measured with various temperatures. You can actually see the variation of the radiation, rate coefficient using the variation of the rate coefficients with respect to temperature. And with this, what I would conclude is, I will go to, you can ask me, why this laser induced fluorescence you have shown, Rajkumar? The answer is, I will go to my last slide, which explains essentially this one. The bottom line is, when you look at, I have a CRD spectrometer. I have a CRD spectrometer here. Now we are working on the OH radical emissions in the reactions. And the radicals, when they react, it produces a lot of OH. It is not only that it is like ozone in the stratosphere and troposphere. One is good, one is bad. Similar thing, when you are reacting with OH, the reactants loses the identity, and at the same time when radicals react, they do produce OH. So you want to measure the quantum yields of this OH in the radical reaction. We are actually integrating the laser induced fluorescence and the cavity ring down spectrometer. This is our next plan. We are actually working on this. This is one of the exploratory research projects of the IIT Madras. Recently it was funded. And with this, I will just conclude. And take home message is, the complete fate of the compound in the Earth's atmosphere can be investigated in our laboratory using supersensitive laser and spectroscopy. It will not only give these kinetics, but also we can measure the lifetimes, global warming potentials, ozone loss and ozone production, and photochemical ozone generation, and many things we can. Actually, if you give me a compound, I'll tell you what exactly it will produce in the atmosphere. That is the bottom line. This is the laboratory at which IIT Madras we have built in, and fantastic facility. I would proudly say this is one of the top class laboratories in the world for the atmospheric chemistry. It costs about 15 crores of money, and this is the group. This is the group with which we are working on, and I am here because of three individuals, Professor Arunand, and I'm thankful to all the funding agencies, and particularly Farook College today, and Pradeep for giving me an opportunity. Thank you.
Thank you, Professor. Now it's a time for discussion. Participant may ask 2 or 3 quick questions.
In the chat box, chat box, any questions are there? You can see.
No, sir, I can see. So I have one question, sir.
Sure.
So you used computational studies, computational works, which is for kinetic studies only, or to understand kinetic studies, kinetics work. How good is the agreement between this experiment and computation?
Usually, if you give any conditions to the system, what you are working on, the theory, and if you optimize without any pre-inputs, if you get a correct agreement, that is the best possible theory. But it doesn't work like that. You have to actually play with a lot of theories. But most of the times, what will happen is we will not leave till the agreement is good. Certain systems are okay with the DFT kind of calculation. Certain things we need to go for, higher level of GN type of methods. But generally agreement, I would say maximum variation I have seen, maximum, that is 10 to 20%. I think that is very, very minimal in the kinetics. Even the experimental agreements are, sometimes it goes up to 25 to 30% among the reported studies. So I would say they are very good. And also the kinetics, computationally, it will give you the channel to channel, site to site, site specific calculations, kinetics calculations.
Which functional is better for radical studies?
That depends on the molecule you are choosing. Suppose it's a simple volatile organic compounds and all, your DFT with a CCSDT energy minimization would be fine. In DFT, many functionals are there. You need to play around. I mean, we cannot simply say this is the best for every molecule. For example, aromatic molecules, M06 method was very, very good. And if I use B3LYP functional, it was not at all matching. That is the kind.
Thank you, sir.